So chapter 20 is fun because it's chemistry. And in chapter 20, the two main things we want you to know are how to balance equations and like what they actually mean and symbolize, and also energy reaction diagrams. Okay? So first thing though, balancing equations. This is probably the one thing you remember from high school chemistry if you took it, which is good. So this is our classic poster boy for chemical reactions. Hydrogen and oxygen and gas combining to form water. This is a fun reaction. It explodes. We like explosions. First, just want to really quickly go over what these symbols mean. Okay? So subscripts tell you how many atoms per molecule. Okay? So for example, if I wanted to draw H2, pictorially it would look like this. A hydrogen atom bonded to another hydrogen atom. Okay? Oxygen, similar. Two oxygens bound together. Okay? In H2O, this tells me I have two hydrogens for every one oxygen atom in a molecule. Okay? So it looks like this. So now you notice if you count the number of atoms of each kind on the left and the right, they're not the same. So in chemistry, chemical reaction cannot create or destroy atoms. Okay? So if I have two oxygen atoms on the left, I have to have two on the right. And notice this isn't the case in this reaction yet. So we have to make that balanced. Okay? So how I like to do it, one way to do it is to draw pictures and count the pictures. Another way to do it is to draw a table. Okay? So we have our table, and we list all the atoms in the reaction here. So we have an O, and I have an H. Okay? And then on our left, this side we call our reactants. And on the right side, we have our products. Okay, so on the reactant side, we have two hydrogens, okay, and we have two oxygens, okay. And then on our product side, we only have one oxygen, but we have two hydrogens, okay. So we need to do something so that this is balanced, okay. How we balance chemical reactions is we put big numbers out in front. The big numbers out in front tell us how many molecules we have total. So if I put a 2 out in front of this, okay, now I have two separate water molecules. You can kind of see, imagine there's parentheses around that, okay? So now I'm adding another water molecule to my drawing. So now we want to update our table. So now on the right, one way you can do it, you can just draw it out and count. Or you can multiply, so 2 times 2 is 4. So I'm going to have 4 hydrogens on my right. Update that to a 4. And I'm also going to have 2 oxygens. Okay. One way you can do that is by drawing, or a 1 is always assumed here. We don't write it because it's typically unnecessary. So we kind of, but just always know there is an assumed 1. So 2 times 1 is 2, but we just typically don't write that. So now our equation is still unbalanced. Our oxygens are balanced, but we need to balance our hydrogens. So now, on the left, we have 2, but on the right, we have 4. So what we can do on this side is put a big 2 out on front. Okay? Now that means I have 2 separate hydrogen molecules. So now I have 4, and now it's balanced. Energy reaction diagrams. To this day, I still not quite sure to call them energy reaction diagrams or reaction energy diagrams, but it doesn't really matter. They are the things that tell you about energy. So, how we draw them, here this axis. Our x-axis, you can kind of think about it as energy, but it's more like chemical potential energy, or the energy in bonds. Okay, energy in the bonds in the molecule. Okay, so then our y-axis is extent, or progress, or time of the reaction. Okay, so then when we draw these, we have this dotted line, and this dotted line, or dashed line, tells us the energy in the bonds that we start out with, so our starting line. Okay, so now what we want to do is let's do the energy diagram for this reaction here. Okay, the combustion of hydrogen and oxygen gas to create water. Okay? This is just the most often used example reaction. Look it up on YouTube. It's pretty entertaining. So first what we're going to do is we have to put some energy in to our molecule to break the existing bonds. So the energy goes up. We call that the activation energy. Okay? That's how much energy I need to start the reaction. So once we put in the activation energy, all the bonds, or at least the necessary bonds, are broken. Okay? So for this reaction, the bonds between the hydrogen and oxygen atoms are broken. So I would just have free hydrogen and oxygen atoms just floating around. Okay? Now, then what happens is they form new bonds. So in this case, we're going to form the bonds, oxygen and hydrogen bonds, necessary to make water. Okay? When this happens, it turns out that the energy stored in the bonds in water is less than the energy stored in the bonds of hydrogen and oxygen gas. Okay? So we draw a line, it swoops down, we draw it down below our initial starting line. Okay? Now remember from previous units and chapters that energy is conserved. So I can't just like poof it out of existence. The energy that used to be in these bonds can't just like die or something. Okay? What happens to it is it comes out, okay, as heat, light, and happiness. Heat, light, and happiness, because you'll find that deep down all chemists are pyros. So in this reaction, if you look it up on YouTube, we get a nice big fireball, and it's fun. Okay? So all reactions that end up giving off energy, we call exothermic. So the root words for this, exo meaning exit, and thermic meaning heat. So heat is going to exit this reaction. Okay? So whenever you end up with the line below the starting line, it's always going to be exothermic. No matter what else happens over here, if it ends up below where what you started, it's always exothermic. Okay? So now what we're going to do is I'm going to show you an example endothermic reaction. It's the other type of reaction we talk about. And in an endothermic reaction, we see something a bit different. Okay? So same X and Y axes. But in this case, so all reactions are going to start out with some activation energy. Okay? You always have to break some bonds so that you can form new bonds. Okay? So then what we do, but in an endothermic reaction, the final energy stored in the bonds of my new molecules is greater than the energy that was stored in the bonds in my reactant molecules. So the energy stored in my product is greater than the energy stored in my reactant. When that happens, we end up having, remember, energy is conserved, so we actually end up having to put in energy into this reaction. Okay? So this symbolizes the energy we have to put into the reaction. Okay? Now these reactions will not emit energy. They will take in energy, so they're going to, if you touch them or touch the vessel containing them, they'll feel cold. And we call these reactions endothermic. Okay? Endothermic reaction. Don't really know what the root word for endo is, but it's just the opposite of exothermic. So these reactions are endothermic. So any reaction where I end up above my starting line is going to be endothermic. Any reaction where I end up below my starting line is going to be exothermic. Okay? So before we're done, there's one more thing we need to talk about, and that is catalysts. Okay? Catalysts are really important. Without biological catalysts called enzymes, all life would cease to exist, because the reactions in our bodies that like make us move and digest food and like think and stuff wouldn't happen fast enough for us to do any of those things in the time that we need to do them to actually like move and do things. So, very important, catalysts. One thing that is important, other than exothermic and endothermic kind of labels for reactions, is a reaction is energetically favorable or not energetically favorable. So when we talk about being energetically favorable, everything in the universe is fundamentally lazy. Okay? So all atoms and molecules and the electrons in those bonds want to be at the lowest energy state possible. So in an exothermic reaction, they get to do that. So they start out at a higher energy, and we put in some activation energy, but they end up at a lower energy, okay? And that decrease in energy gives us heat and light, but it's also what they want because they're now at a lower energy state. So we call exothermic reactions, we also say that they are energetically favorable. After the zombie apocalypse, what reactions would you want to use to heat yourself in the cold? Reactions that take in energy, like endothermic reactions, probably would not be a good choice. You would want to use exothermic reactions, okay? Because those are energetically favorable for you, kind of think about it, because they end up giving us energy and allowing the atoms and electrons in those bonds in the molecules to end up at a lower energy state. One thing we like to use energy reaction diagrams for is to compare reactions, okay? So for example, if this reaction that I have up here is the combustion of hydrogen and oxygen to make water. Now this reaction is explosive, it's fun, but there are reactions that are much more explosive. Thermite is one of these reactions, but with thermite, we need to start it with to burn a magnesium strip. Magnesium ribbons, they burn super bright and super hot. And that tells you that reaction is going to have a very high activation energy. If we were wanting to plot the energy diagram of thermite, it would look much different from this. It has super huge activation energy, okay? You can't even start a thermite reaction with a blowtorch, okay? Super high activation energy. But you get a lot of energy out of the thermite reaction, much more than you get out of hydrogen-oxygen combustion. One way we use these energy reaction diagrams is so we can pictorially, and also we can do a lot of math with these, not in this class, but in other classes, okay, to compare activation energy and how much energy you get out of these reactions, okay? So in this chapter, what we learned is we learned about balancing equations and strategies to do that. We also learned about energy reaction diagrams. We have exothermic reactions and endothermic reactions. We also learned about how we can use these diagrams to compare reactions. So reactions with a higher activation energy are going to have a higher hump here, and that give much more energy out are going to have much bigger distance here. And that's about it.